Good morning. Welcome to our meeting. So last week we didn't have a meeting, we had an admin meeting instead, and it was private. We discussed some of the directions forward for what we'll be doing in the fall and in the next year coming up. No hard and fast plans, but we are planning on having at least one event, public event, as well as participating in the active inference symposium for this year, which I'll talk about in a little bit. So in terms of our meetings this week, we had one DevoWare meeting. This is our GitHub archive of the DevoWare meetings. Since we didn't have a meeting last week, I'll talk about both last week's meeting or the week before's meeting and then last week's meeting. So the week before September 1, I did a summary of our activities. That was the day when all of the Google Summer of Code projects were due. And so I gave a tour of both DevoWorm or DevoGraph submissions for GSOC. So congratulations again to Jayadratha and Leilith Baru for their work this summer. They both did, I think, a very good job and properly submitted their research. And so we went over those repositories. And if you go to the meeting notes, you'll see a link to the repository. Then in addition to that, I talked about this new paper that discusses a neurite-based developmental connectome. So in Jayadratha's project specifically, he cites this data set from Whitvliet et al. I think it's from 2021. And they have this developmental connectome with synapses specified. So you have the larval stage worm as it develops through its different larval stages, and they're able to track the synapses and the change in synapses over that time. And so that's relevant to this new paper because this new paper proposes a neurite-based developmental connectome where neurites are the projections from one cell to another. So they're able to actually track those. So instead of just having a connectome that describes connections between cells, we actually have some of these new details from larval development that talks about some of the things going on in this rather lengthy stage of C. elegans life history. And so that was a very interesting paper. I'd go back to that meeting to check out some of my comments on it and some of the details of the paper. So that was September 1. Then last week, September 8th, or rather last Monday, we discussed a couple of papers on the mathematical modeling of cell deformation and another paper on biotensegrity and superstability. So Susan has this long-standing interest in working on tensegrity models of the cell and working out mathematical modeling of the cell mechanics in a epithelial sheet or some other structure that you'll find in developing embryos. And she offered some papers that she ran across, and then that led into our discussion on biotensegrity and superstability. Now that latter paper is really interesting because it offers a lot of insight into sort of a tensegrity model for biology. And this is something that Susan has been having trouble finding because most people work on tensegrity structures. They work on things like architecture or mechanical systems. And those aren't suitable for biological systems. This is a paper by some experts in the area of biotensegrity, some big names, such as it is. And they offer this model of biotensegrity as a fundamentally different set of things than what you would find in a tensegrity structure. Mainly that there are these closed kinematic chains that propagate forces throughout the structure, making it super stable and unlike maybe a mechanical structure. So check that meeting out. That's a good meeting, especially if you're interested in that area. So the next thing I'm going to talk about is something that Morgan posted in the Slack. This is an upcoming conference called Metagame. This is a conference about game design, strategy, narrative, and play. This is being held, I guess, this weekend in Berkeley. And so I don't know what the details are here. We'll look in a minute, but this is an interesting event where they're looking at these kind of different types of games, like board games and card games, video games, tabletop games, puzzles, rock climbing routes, that's interesting, and more. And so it's basically answering the question, what would the consumer of this experience choose to do next? So that's kind of what they're doing, and it seems like it's both a social event and a conference. The speakers include, I'm not familiar with any of these names, but they're from various companies and organizations that do things in this space. So thanks to Morgan for pointing that out. There's also this Crowdcast event. This is something that happened this week, but you can watch the replay. Crowdcast, this was hosted by Worldwide Neuro. We haven't talked about Crowdcast in a while, but there's still content being published on Crowdcast. And this is a seminar that is going to talk about the evolution of brain cell types. So we've talked about that in the meetings before and how to define those and their relevance to cognition and neuroevolution. And so these are two speakers here, Maria Antoinetta Toches, who will be speaking on the evolution of Cajal-Retzia cells by cell type neofunctionalization. And the second speaker is Paul Katz, Cell Types versus Cellular Identities and Nudibranch Mollusks. And so that looks like it's quite interesting. They're 20-minute talks apiece. So check that out when you have a chance. Now, I wanted to talk a little bit about the 5th annual Active Inference Symposium. So last year we participated in the 4th symposium, and we had a nice set of talks. I hosted a talk where I interviewed Stefan Bollman, who's involved in various open source efforts in the neuroscience analysis community and the neuroimaging community. So he's interested in reproducible research software and some of those initiatives. And the video where I interview him is on our YouTube channel, but of course there's another version that is part of the symposium that's on the Active Inference YouTube channel. We also talked about open source and open access. I gave a lecture on that, and that is also available on both YouTube channels. And a lot of interesting points that I raised last year that I'm going to try to transfer to this year's set of presentations. And then Jesse, of course, gave a short presentation, and that's also on our YouTube channel on some project management things. So for the 5th annual symposium, which is coming up in November, early to mid-November, I think it's like the 12th through the 14th. Yeah, there it is. And so this is free to attend. This is virtual, and we have a couple of submissions already. I decided that we were going to talk about spatial cognition and agents and cybernetic regulation and things like that. This kind of arose from a discussion I had with Adam Safran about how spatial cognition is really maybe the root of cognition in animals. And so, I'm going to talk about that a little bit. I don't know what that's going to look like yet exactly, but we're working on that. I also wanted to give an update on the open source sustainability project. So this is the project that we've been working on over the last few summers with different GSOC scholars, but also things that we're trying to get off the ground with respect to our agent-based modeling and our computational agents work. So, it'd be a nice opportunity to kind of put that in a larger context for people and see if we can get some additional interest in that area. And we can still, and I would like to, interview someone from our open source reproducibility community I don't know. We talked a little bit in our admin meeting about possible names. We have possible names from last year, so we might follow up with another interview. We'll just have to schedule that interview and see, how that shakes out. So we have a plan going forward. We need to get some things done between now and November at the time of the symposium. And if you're interested in participating, let me know. In terms of the symposium itself, we're not really there yet in terms of an agenda, but you can look at the symposia from past years. In 2021, it was largely like a Carl Friston exercise. In 2022, there was a robotics theme. In 2023, it was enacting ecosystems of shared intelligence. In 2024, the theme, I guess, was applied active inference. And then this year's theme, I don't know what the theme is this year, actually. I don't really think that there's a theme that's been settled on. But in any case, it doesn't matter because anyone working in active inference or in a wide field is invited to give a talk. So if you're interested in participating, there's the symposium link. You can fill out a submission form for submitting researchers. You can also sponsor the symposium if you're so inclined, or you can register just simply as a participant. You can go onto their YouTube channel and join the live stream, or you can go into the Zoom. It's usually the live stream is better for casual participants. This is another article that was posted in the Slack. I think it may have been Jesse who posted this. But it's really interesting with respect to reinforcement learning. And so it's from Decisions and Dragons, which I think is a blog online. And so they ask the question, and when you motivate something with a question, the answer is always no. So the question here is, actually it's two questions in the title. Should we abandon reinforcement learning, or RL? And then, is it the right approach? So we're going to answer both of those questions here. So the answer to the first question is no, we should not abandon reinforcement learning. I get it though. Reinforcement learning algorithms are brittle, difficult to scale, and complicated. However, this question is predicated on a misconception. Reinforcement learning is not an approach. Reinforcement learning is a problem definition. So it's a different kind of maybe way of thinking about reinforcement learning and reminding us that it's a problem definition more than a means to an end in terms of learning. Reinforcement learning is the problem of determining how an agent should make decisions in an unfamiliar environment. It must act to both learn about its environment and pursue its objective. It must learn from its experiences rather than human-curated data sets. We don't abandon problems. They are imposed upon us and we ignore them at our peril. Asking if a problem is quote-unquote right isn't a coherent question. What is a coherent question is whether a problem is important or relevant. So I would also add to that whether the question is salient, meaning that is it something that's within your view. So you might think something is important, but if that question is not in your view, or a good form of that question is not in your view, you can't really answer it. Something might also be relevant, which means it could be important, but not relevant and be ignored. So there are all these different aspects of questions. RL is an important problem. If you care about building systems that can act and learn in the world like people do, then reinforcement learning, that problem is impossible to avoid. The question is not whether we should abandon reinforcement learning, but how we can make better algorithms to solve it. So this person cites the Sutton and Bartow textbook, and this person thinks that RL is a problem rather than an approach, and that's not a controversial idea. And if we go into the Sutton and Bartow book, in the first chapter, they say, reinforcement learning is defined not by characterizing learning methods, but by characterizing a learning problem. Any method that is well suited to solving that problem we consider to be a reinforcement learning method. So if we hope to solve the reinforcement learning problem, we must not conflate it with common methods to solve it, nor with overly specific formalisms of it. Achieving success might depend on someone coming up with a unique perspective that we haven't yet considered. So they point out that reinforcement learning is not limited to model-free methods. So it isn't just limited to things like Q-learning and SARSA. Well, the reinforcement learning problem requires the agent to act without initially knowing how its actions will affect the environment. There is nothing about the reinforcement learning problem itself that prevents the agent from learning a world model and planning with it. In other words, model-based reinforcement learning still solves the RL problem. But, of course, model-free reinforcement learning, there are good reasons why that has not been predominant. So, learning a useful world model turns out to be challenging. And choosing the right kind of world model training objective can be tricky. So how do you optimize for feature level accuracy? And, how do you make trade-offs when you do that? Well, sufficiently accurate feature predictions will allow an agent to plan well. In practice, even small errors tend to result in a poor model for planning. What we really want is an objective to make good predictions of future rewards, conditioned on different counterfactual actions. We want something like a Q function loss that is estimated through a world model. A practical implementation, of course, is harder than it sounds. There are newer algorithms like Dreamer v3 and Mu0 that show that MBRL is getting better. This is model-based reinforcement learning. And with the broader AI community taking an interest in world models, there are people working on this problem, more people working on this problem than ever before. Myself and many others believe that doing model-based reinforcement learning right may be the key to cracking the reinforcement learning problem. So don't limit your approach to model-free methods. So one of the main methods used in reinforcement learning is generalized policy iteration. In this method, the algorithm estimates the value function and uses it to improve its policy. So Q-learning, SAC, and PPO are all GPI methods, or generalized policy iteration methods. Even model-based approaches like Dreamer v3 and Mu0 have this generalized policy iteration sitting on top of a world model that's been learned by the model. Generalized policy iteration is popular because it tends to yield the best results and it has various appealing properties. However, just as the reinforcement learning problem does not restrict us to model-free methods, it does not restrict us to generalized policy iteration either. So, is this a dead end or not? Well, we don't really know, but, there may be other options. So there are a number of options that we could take for non-GPI methods, which maybe include evolutionary algorithms, upside-down reinforcement learning, or decision transformer styles. And these are just methods that exist in the literature that might work better than generalized policy iteration. And of course, meta-learning, which is where the agent learns to learn. You can apply almost any black box optimization method to a reinforcement learning problem because the black box optimization problem is even more general than the reinforcement learning problem. And then they point out that reinforcement learning is not limited to Markov decision processes. You may be excused for thinking that reinforcement learning is about solving Markov decision processes, but it's not. Not only are there non-Markov decision process reinforcement learning formulations, most Markov decision processes fall in the category of planning rather than reinforcement learning. And so they point to two examples which are partially observed Markov decision processes, or POMDPs, and stochastic games. And both of these methods generalize Markov decision processes where the agent must rely on a memory and take explicit information gathering actions even after it's familiar with the environment. Stochastic games also include multiple agents acting on their own interests that may or may not align with each other. And this is something that you can use in various ways to augment reinforcement learning. And there are other variants available. The ones that I mentioned are more convenient in terms of their implementation, but there are other possibilities. So one of the other problems with reinforcement learning as a problem to be solved is that it's somewhat vague. So it's hard to really get a handle on what is included in the reinforcement learning problem. But of course, it's no worse than anything else that we use for learning, such as supervised learning. Like reinforcement learning, supervised learning is a vague definition by design. It allows for a bevy of formalizations and an even greater variety of methods to solve it. You have Bayesianism, maximum likelihood, probably approximately correct, optimization, and so on. There are even people attempting to apply Dempster-Schaeffer theory, which I think is interesting because that has implications for belief structures and other things like that. Despite that, supervised learning remains useful high-level problem description, and as the same is true for reinforcement learning. And what's interesting is that people have made connections between reinforcement learning and control theory, where people have sort of objected to reinforcement learning because they think or they feel that it's reinventing control theory. And indeed, there's a lot of overlap in what you're doing. You're essentially building things on feedback, and you're building things on sort of optimization. So basically, it has the same structure as control theory. Actually, it's interesting is that cybernetic control so has that kind of structure. And if you go to our recently minted archive paper on the Evergood regulator theorem, we raised some of these issues in that paper. And so you might ask, why splinter from control theory? But, maybe that it offers different types of benefits. Maybe it needs to be unified into a general theory of control or a general theory of feedback. It's hard to say. But while control theory work provides a mathematical foundation for reinforcement learning, the field for the most part does not focus on the reinforcement learning problem. Control theorists are interested in engineering, in systems dynamics, in figuring out control laws that they can write down and apply to an engineering system. In reinforcement learning, however, the focus is on an agent that must learn about the system and how to control it on its own through interaction. So there's this fundamental difference there. So if we think about control theory being exercise in systems identification, we find that systems identification often fits the parameters of a human-engineered physics model. Even when his model is a black box like a neural net, the data used to train it is usually assumed to be provided up front. You don't have this focus on acting, learning, and collecting data like you have in reinforcement learning. And so there is this distinction with a difference. So that's enough about that article. I think it's very enlightening in terms of some of the things we've been doing with reinforcement learning and some of the things we've been exploring with cybernetics and the links to control theory and to partially observed Markov decision models, and then by extension, active inference. Now, this is something that Morgan posted on LinkedIn, and we had a discussion about it online, and I wanted to kind of point this out. So this is a talk by Alexander Shaw from the University of Exeter, and this is just kind of a preview where he talks about active inference, a neuro-inspired blueprint for general intelligence. And this kind of gets into the free energy principle and intelligent agents and all this. So it kind of goes over how active inference is related to AGI. So why does active inference matter for AGI? And so he says any system that persists, which means it continues for a long time, it continues despite perturbation, it continues despite changes in the world, must avoid disorganizing, or what in active inference and in free energy principle we call surprising states. Biological agents do this by building models of their world, inferring hidden causes of sensory data, and acting to make future data match their predictions. So this is a definition of active inference, where there's this core decision objective, which is governed by free energy, and agents acting upon that update beliefs to explain data that they gain through perception, and select policies to make data predictable, which is their action, and jointly minimize the expected free energy of perception and action. So they use this expected free energy and they minimize it as a product of the joint distribution. And so why this matters for superintelligence, as they define it in AGI, it gives a unified objective, so one principle drives perception, learning, exploration, and control. There's built-in curiosity, so exploration emerges intrinsically. There's model-based and embodied aspects, so you learn a world model and use it for inference, planning, and action. And it gives us a scalable architecture that we can use. And so it looks like he did a study on Pong where they did some work showing this active inference agent interacting. And this ties into a lot of things we've been talking about with dish brain and organoids and organoid intelligence. So that's kind of where the application is. But also you can look at computational agents and use a similar framework. So a couple of papers from Alexander Shaw's website. This is the first paper, a neuro-inspired computational framework for AGI, predictive coding, active inference, and free energy minimization. So the abstract reads, this paper proposes that foundational principles for theoretical neuroscience, we go predictive coding, the free energy principle, and variational inference, offer a biologically grounded framework for artificial general intelligence, or AGI. These approaches characterize the brain as a hierarchical inference system that continuously updates beliefs and selects actions to minimize uncertainty and surprise. In contrast to conventional AI systems, which typically rely on static architectures and offline training, biological agents engage in active generative inference within dynamic, uncertain environments. We argue it is this inference-based architecture, not just its behavioral outputs, that underpins the adaptability, generalization, and resilience of natural intelligence. And so they outline a neuro-inspired framework for this using variational Laplace and active inference. Finally, we contrast this approach with dominant deep learning paradigms and discuss its implications for building interpretable, adaptive, and autonomous machine intelligence. So they kind of walk through some of the background, and they come, they kind of focus on predictive coding and the free energy principle as sort of the basis for this. Building a predictive loop that supports both epistemic behavior and instrumental behavior. So epistemic behavior is where you reduce uncertainty through exploration, and instrumental behavior is where you pursue preferred outcomes. And this predictive loop is achieved internally by simulating possible futures and evaluating them according to expected free energy. Variational free energy is defined by this equation, which is an where you basically have the KL divergence minus the log value of model evidence. And we can look to the brain as a model of general intelligence and, use this model, which models what's going on in the brain, as a biologically inspired approach to superintelligence to AGI. So this is the second article, Predictive Coding in Neurocomputational Psychiatry, a mechanistic framework for understanding mental disorders. And so, we're interested in computational psychiatry in this group, so I wanted to talk about that a little bit. The abstract reads, predictive coding offers a powerful computational framework for understanding brain function and psychiatric disorders at a mechanistic level. This perspective synthesizes advances in computational psychiatry, proposing that mental disorders can be conceptualized as specific alterations in the brain's predictive inference machinery. We first outlined the theoretical foundations of predictive coding, including Bayesian inference, free energy minimization, and neural population dynamics, showing how these abstract computational principles map onto specific neural circuits and biophysical mechanisms. We then demonstrate how diverse psychiatric conditions can be understood within this unified framework. Critically, this additionally provides a basis upon which predictive coding becomes a testable, modifiable, falsifiable construct within biological psychiatry. And so then it has clinical applications, and by grounding psychiatric symptoms in aberrant predictive processes implemented in neural circuitry, this approach promises a more mechanistic understanding of mental disorders and a path towards more targeted, effective interventions. And so computational psychiatry is defined here, offers a new paradigm by integrating mathematical models with neurobiology and explaining psychiatric phenomena in terms of aberrant brain computations, so computations that deviate from normal computations as defined experimentally. And so how do we get these brain computations? Well, we use something like predictive coding, which allows us to derive sort of a normal course of learning, and then look at how there's sort of variation in that. They're variational methods. This framework provides a normative or Bayesian account of perception and action, where the brain tries to minimize surprise or free energy. So this free energy has this surprisal factor, which is roughly the same as information entropy in information theory, by aligning its internal model with the outside world. And so this is, again, what we do in closed-loop cybernetics, where we're looking at matching between the model and the world. Crucially, this perspective offers a plausible account of neuronal computations and cortical circuits. Hierarchical networks of neurons are thought to exchange top-down predictions and bottom-up prediction errors to achieve efficient information processing. And so he goes on to kind of review computational psychiatry and showing kind of these different mechanisms here. And then he walks through the math of predictive coding, Bayesian dynamics, and then some other things having to do with neuroimaging, and then coming up with a biophysical generative model, which kind of touches on Hodgkin-Huxley, and finally coming up with a neuronal circuitry of predictive coding, where you can look at these hierarchical predictive coding models where every cortical area or layer of neocortex has units that encode the current prediction of some features and units that encode the prediction error or the unexplained residual. So the error is the residual, the prediction, the main prediction is supposed to be the main thing that the model operates on. Psychologically or physiologically, a plausible mapping is that deep layer pyramidal neurons carry top-down predictions to lower areas, while superficial layer pyramidal neurons carry forward prediction areas to higher areas. So he gets into a number of examples from psychiatry. The first is obsessive compulsive disorder, which is an overactive error signal and precision problem. So you basically have this differential equation that describes obsessive compulsive disorder. You have anxiety disorders, which are defined as exaggerated uncertainty and threat predictions. We have this evolution equation that describes that. And then bipolar disorder, or the instability of precision and network dynamics, which is again this couple differential equation, but in this case using different things as inputs into it. So the idea is we create these mathematical models, these computational models. We investigate the phenomena so we can get the data to serve as inputs to those equations. And we can maybe perhaps predict different clinical states as functions of the brain, as well as use these models like predictive processing and predictive coding to yield insights into the circuitry. So I wanted to go over this blog post. This is by Amahury Diaz, and this person is otherwise known as Complexity Cat. So Complexity Cat is on Blue Sky and other platforms, and they posted this post on computing, especially with respect to what does computing mean. So this is kind of something we've revisited when we talked about physical computation, and when people talk about computers and the brain, or computers and biology, or computation and biology. Usually people are talking about computational processes in biology or the brain, and they use the term computing. And then that's allowed for there to be this large-scale debate about whether the brain or biology actually computes. And I'm not sure that a lot of people who use the terms intend there to be this huge debate, but when you don't have a precise definition of what you mean by computation or computing, this is what tends to happen. Now, the reason why it's controversial is because there is actually a very rigorous definition of computation or computing. The problem is it's not necessarily applicable to biology or the brain. So, the one definition that we sort of agreed upon is the Church-Turing thesis, or the Church-Turing-Deutsch thesis, which have a specific definition. And when you say computing, usually people mean some computational operation where you're maybe adding things, or multiplying things, or subtracting things, or comparing things. And those are not, those are maybe not what we think of when we think of computers or modern computers. So I think that the way it operates in practice is a little bit divorced from the more formal definitions. So that's why I found this essay so interesting, because it gives this perspective on this and allows us to kind of think beyond maybe the pan-computationalist approach that we've kind of settled on with respect to the way we think of applying computational biology in the brain and other natural systems. So this starts the concept of computation, as we now understand it, has deep historical roots. Originally tied to the human act of calculation, its meaning expanded alongside developments in mathematics, logic, and engineering. Early mechanical devices, such as Pascal's calculator or Babbage's analytical engine, embodied a physical form of computation, but it was early in the 20th century the notion became rigorously formalized. And that definition is a well-defined transformation of symbols into symbols, or into other symbols, attached from matter, time, and energy. This is, I guess this is consistent with the Church-Turing thesis, or at least a lot of the modern computing applications that we've built. So we've built computers. Computers just don't come out of the sky. They're not natural things. We have to build those things, but we have to build it based on an idea of what we want to produce with them. This abstract framing is reflected in standard references that define computation in terms of algorithms, models of computation, and classes of solvable problems. So these again are sort of the fruits of computation, or at least the languages of computation. And so when you do something like computational biology, if you're saying that the cell computes something, you have to propose a natural algorithm. You have to propose a natural model of computation. And you have to have classes of solvable problems. And we're kind of moving in that direction with synthetic biology, with some of there have been books written, some decades old, that have proposed natural algorithms for things like gene expression and other types of processes in the cell. But this is not, this is just kind of our interpretation of what's going on. It doesn't mean that that's something we can actively go in and hack. Although, we have some systems in the cell which you can actually, that are, I would argue, hackable. So this is one, this is a nice rigorous definition of computing, but of course, it's, kind of a one definition of computing, and there are other definitions. We talked several weeks ago about sort of a neurological Turing test, or a neuro-Turing test, where a Turing test for behavior and the outputs of the brain. And that was interesting because it bore some sort of resemblance to the work of Alan Turing, but it wasn't exactly what Turing had in mind when he talked about a test of computation. So moving on, at the same time, contemporary debates ask whether such a disembodied view is enough, especially once we notice how often the concept of computation migrates across domains, from silicon circuits to living cells to chemical reaction networks, giving rise to this term Pancomputationalism, which is a term that encompasses this idea that computation is at the root of all natural systems. So a lot of times, actually, the person who proposed Pancomputationalism it was proposed by Friedkin, and Friedkin was a physicist who basically argued that all of nature essentially was computational, or at least all of physics is computational, and then that extends to all of nature. So, this is kind of framing this in this historical framework. And of course, now Alan Turing is discussed in this article. Working within a scientific culture enthralled with mechanization and reduction, Turing gave a canonical analysis of effective procedures by his abstract machines. And these are machines that he designed that kind of allowed a lot of computation to happen, artificial computation. As Sidney Brenner pointed out in Life's Code Script, Turing's work became a huge influence from logic to morphogenesis, underlying how a mechanistic picture of symbol manipulation became a lens for the life of sciences as well. Less well known outside specialist circles is how closely Ludwig Wittgenstein tracked these developments. Over the 20th century's most significant philosophers of logic, mathematics, mind, and language, Wittgenstein was not only contemporaries of Turing at Cambridge, he also responded pointedly to the philosophical reading Turing attached to his mathematical results. So this article here is a nice article that kind of summarizes this. Wittgenstein versus Turing on the nature of Church's thesis. And this is kind of a sort of a dialogue between Wittgenstein, and that Wittgenstein knew of Turing's work and engaged in its implications for the very meaning of effective calculation. So underlying computation is this idea of effective calculation. It's kind of an interesting way to summarize what's going on, and it's a way to link the philosophy with the actual sort of mechanisms of computation. This is a conversation that continues to unsettle how we answer the question this essay title poses, which is, what does computing mean? The author of this article is reminded of Robert Rosen's insights on computability and realizability. And so, this is something that there's a connection between Rosen's work and this debate, or I guess this dialogue between Wittgenstein and Turing. So you have Wittgenstein, Turing, and Rosen kind of all contributing to this kind of view. So the whole point of this article isn't just to kind of introduce this problem, although it's you could write a lot on that. And we did a couple of meetings, I think in 2023, where we talked about physical computation and then kind of moved from that concept to sort of the application of computability to biology, and we hit upon a lot of these issues. But what this author is trying to do here is trying to find the major epistemological gaps surrounding the concept of computation. A lot of times people haven't addressed these directly, and so like I said previously, sometimes people take this metaphor and they apply it, and they don't think about it critically. So there are a lot of things that are maybe actually supportive of the notion of biology being computational that people aren't engaging with. They're just simply engaging with the metaphor. And so then that means that the work suffers from this sort of interpretation that biology is like a modern computer, that it's like a von Neumann computer, that it has like a very specific type of sort of set of mechanisms and architecture that life simply doesn't have, although life might still yet be computational. So this discussion of what computation is, of course, has to go back to Turing machines, since that's our modern definition of digital computing. And Turing machines are idealized devices that read and write symbols on an unbounded tape according to finitely many rules. As an abstract analysis of calculation, this framework has been enormously successful. Yet, as Shankar emphasizes, Wittgenstein's scattered remarks force us to read Turing's 1936 achievement with more care. So Wittgenstein knew of Turing's uncomputable numbers work, but he left a puzzling gloss in his remarks on the philosophy of psychology, Turing's machines. So, according to Wittgenstein, Turing's machines these machines are humans who calculate. He then downplays the specialness of the halting problem, treating it as no more philosophically momentous than familiar paradoxes in the foundation of mathematics. The author of this dialogue between Wittgenstein and Turing takes this puzzling note as a point of entry. So it directs us to separate Turing's strict mathematics from the metaphysical freight that later came to be carried under its banner. So Wittgenstein was thinking about this earlier than Turing, but also then was in the position to sort of critique what Turing was doing and have this dialogue. So if we go back to the 1930s, which was before Turing's work on the Turing machine, Wittgenstein had framed a specific question, which was, can a machine think? And so that question is a category error until we clarify some of our concepts, because we have to say what thinking means and what a machine does to think. So this is interesting because Wittgenstein also made this comparison by asking if number 3 has a color. And so the number 3 doesn't have a color unless you specify what the number 3 is, if it's a shape, and then it can have, that shape can have a color. So this is kind of a, you have to specify things more clearly. Second, the mechanist thesis itself was in the air well before Turing's technical work. Wittgenstein's contemporaneous remarks showed him probing the grammar of thinking and pain. So Wittgenstein used a lot of human metaphors of human behavior, human emotion, and so forth. These points explain why, for Wittgenstein, Turing's 1936 paper looked like a hybrid mathematical logic on one side, philosophy of mind on the other, and why he focused his criticisms on Turing's prose interpretation rather than the formal results. So if we just read Uncomputable Numbers, which was Turing's landmark 1936 paper, as a piece of mathematics, we find that once a class of functions is effectively representable, say in some sort of binary form, one can give an abstract recipe for a device whose symbolic operations will compute those representations. The main point is not that a machine thinks, understands, or intends as it executes the rules, but that there exists a finite determinate specification whose iterations produce the right results. So Turing doesn't use a lot of cognitive terminology, and maybe that's to his benefit. Nevertheless, his analysis illuminates the link between recursion theoretic definitions and mechanical executability. So Robert Rosen kind of picks up the mantle much later and kind of builds upon what Wittgenstein talked about in some of his work, independent of Turing, and then in his responses to Turing. Rosen kind of gives a caution here, and that is if we treat Church's thesis as a bridge from the mathematical notation of recursiveness to the physical notation of realizability, we must add physics back in. So if we are explicit about the physical nature of it, we have to bring physics back into the mix. As Rosen argued in Church's thesis and its relation to the concept of realizability and biology and physics, which is this article here, this is from 1962, and this kind of goes over this argument that an attempt to characterize the physical realizability of an abstract mapping process in terms of the Turing computability of an associated numerical function is described. Such an approach rests heavily on the validity of Church's thesis for physical systems capable of computing numerical functions. This means, in effect, that one must investigate in what manner Church's thesis can be converted into an assertion concerning the non-existence of a certain class of physical process, which is where some process can calculate the values of numerical functions which are not Turing computable. And so this is basically taking the idea of computation, kind of moving away from the Church-Turing thesis and kind of thinking about this as a separate thing. So in this paper, Rosen argues that the slogan effectively calculable equals recursive, which is a term that was kind of extracted from this idea of effective computation, has no physical content on its face, and to use it as a criterion of realizability requires restating it as a claim about which classes of physical process exist. As Rosen showed, this is only true given strong assumptions about the laws that govern physical state change. In other words, without such assumptions, Church-Turing is a convention in recursion theory. With them, it becomes a substantive empirical proposition vulnerable to how nature actually behaves. So this is kind of like what Rosen's trying to set up here is Rosen's trying to make this link between nature and computation, but kind of getting around the Church-Turing thesis and that rigorous definition of computation, but also saying that there is this actual model of computation we can use that's much simpler, but we have to bring physics back into the mix to really understand what's going on. Wittgenstein's distinctive pressure point, however, is not physics but normativity. And so normativity is the phenomenon in human societies of designing such actions or outcomes as good, desirable, or permissible, and others as bad, undesirable, impermissible. So it's basically not necessarily this sort of objective physics, but the subjective normativity. To describe a process with a rule is not yet to show that the process follows the rule. Regularity is one thing, rule following another. So if you think about, you say, well, we want to introduce physics back into the mix. And then we think about sort of the regularities that we expect from physics. How do we know that those are actual regularities? And how do we know it's just not rule following that we define by our previous definitions or cultural biases? I guess that's what he's getting at here. The grammar of calculation ties it to the ability to instruct, justify, correct, or explain by reference to the rule. So merely producing the right answers does not suffice to be calculating in the sense that it belongs to mathematical practice. So, again, when we do a computation or we say something computes, is it like something that computes to sort of our expectations using sort of the human language of mathematics? Or does it actually represent some sort of regularity in nature? I guess that's what he's getting at here. It's very, it gets very abstract and subtle at this point. But it's definitely worth thinking about, and definitely bringing Rosen's work into the mix is something I hadn't thought about before. And then of course, there's more here on kind of thinking about computation as sort of anew and thinking about how maybe computation can be applied to biology or nature more generally in ways that aren't sort of pan-computational. So Melanie Mitchell, in her book, The Metaphors of Artificial Intelligence, says that much of what we say when we say that machines learn, understand, or reason is merely a metaphor. Sometimes, we think about machines that learn or understand or reason, and we try to draw analogies from that human process or the biological process of learning, understanding, and reasoning. But those are all metaphors, and we can't confuse the metaphor for the actual thing. And so, we might have something that resembles learning, but mechanistically it's not learning. And so the question then is, are the mechanisms of, say, a neural network the same as the mechanisms of the brain? And if not, are they close enough to just be the same thing? Or are we just making this metaphorical assertion? And there may be important differences between those two types of learning. So that's really what what a lot of the previous section boils down to as well. Schenker's Wittgensteinian reading gives us the sharper edge, which is, if learning is any change that stably improves performance, then nothing categorically distinguishes biological learners from ideal learning machines. So this is where we might have this category of ideal learning machine. And we might compare that with both biological learning and artificial learning and say, what properties do they share? And then there's this idealized form of learning that we can then use as the benchmark or the reference point. So that's an interesting take. Schenker, of course, is the author of that paper where we talked about the dialogue between Wittgenstein and Turing. But, however, what becomes of rule following? Are we committed to a picture in which an algorithm is just a set of trivial subrules whose blind execution yields the right outputs? So, are we just implementing rules that kind of give us the right outputs? Like, in other words, if we take a bunch of biological data and we impose our sort of rules of logic onto them, or we impose a bunch of mathematical operations onto it, we can, in theory, get like the right outputs that give us an answer. So it's kind of like the Chinese room problem, where you pass a bunch of symbols into a black box and you get intelligible symbols out. or intelligible or orders of symbols. But there was no process in there that was cognitive that actually sorted those symbols into something that was intelligible. It was largely by chance or largely by constraint. And so the same holds with rules. If we use rule-like systems to interpret a bunch of biological data, and those data happen to satisfy the rules, then we have this, this computation that nature did. But all, in fact, we did was just apply our norms, our rules, and we got an output. And we don't exactly know why. Or it doesn't necessarily have any larger meaning than conforming to the rules we give it. So Turing had a proposal about learning programs more generally from his work on computation that suggests a way machines can behave intelligently without grasping meanings. Instructions must be complete and explicit. The device need not understand intermediate results, and self-modification can increase competence by reorganizing its store of rules. This neatly skirts the symbol grounding problem, which is where we have this old problem in cognitive science and in AI, where you're basically connecting symbols to real-world objects and using that as sort of a ground truth. So symbols don't mean anything until they're connected to something in the world, and we have to kind of figure out how a cognitive system does that in order to understand, in order to say whether it understands what's going on. So this is, an old problem that people have been talking about for decades. But what we're talking about here is something that kind of gets around it by replacing understanding with execution plus revision. And so in a sense, you can have competence without semantics. So this is just kind of talking more about rules and about following rules as opposed to actually doing computations and engaging in some sort of model of understanding of the symbols that are presented to the system. Okay, so let's go to the conclusion. And so we still ask the question, what does computing mean? Is it this narrow definition of the Turing Church thesis? Is it this discussion between Turing and Wittgenstein? Is it something else that we haven't really considered? And, will we actually be able to use computing or computation as more than a metaphor? So Turing's analysis gives us a crystalline mathematical notation, which is effective procedures realized by a simple symbol manipulation machine. So we have these procedures. We have this, well, first of all, we have this symbol manipulator. It can turn one set of symbols into another, or it can turn some things in the environment into symbols. So symbols are key, but we have to have this process of transformation. And so we have to have these procedures that are regular. And so that's kind of what we could mean by computation. We can mean it's a transformational system that takes objects in the environment, turns them into symbols, or turns one set of symbols into another set of symbols. So if we think about what happens inside the cell, something like translation might be a good example of that. We have RNA, which is composed of the base pairs or the bases of an RNA molecule, and that gets transformed into codons by tRNA. And there's this very complex system where the mRNA enters the ribosome. It gets translated into a set of amino acids, and then it's turned into proteins. So if we think about, and so this biological machine is able to take symbols and turn them into other symbols. You can also have the expression of genes that are turned on, so it can turn a stimulus into a symbol. There are a lot of options here, and by this definition, we could kind of make this case that there's the set of effective procedures that are doing computation in the cell. But of course, that's still kind of a metaphor, because all we're saying is that there's a biological process, and then we're just attaching the name computation to it. So, just thinking about this, we can also go back to Rosen, who adds a caution. If we treat Church's thesis as a physical claim about realizability, we must reformulate it in explicitly physical terms, about which processes do not exist, and then defend the strong conditions it assumes about natural law. Otherwise we mistake a logical grammatical clarification for a statement about the world. So at the formal level, Church-Turing unifies their models of effective procedures, and at the conceptual level, the meaning of computing depends on the role rules play in our practices, and that dependence cannot be read off from causal structure alone. So this is kind of the summary that we get from Rosen. Basically, that we have to think about these procedures in a formal way. Is it computation, or is it just some, action that doesn't do what we would classify as computation? And then, of course, we have to kind of think about rules and how our rules of, say, our mathematical language kind of conform to that. So basically, I don't know, maybe there's a lot of kind of thinking beyond the core problem here. I don't think it is, but one could make that argument. But where does this leave us? So first, that suggests humility about computationalism in mind and life, and by that, I guess the author is referring to a lot of the attempts to sort of map machine consciousness from like a metaphor. So like, you say life does computation or the brain does computation, and the brain is, we have consciousness in the brain, and we have life-like processes. Therefore, we can replicate those in a machine and get similar results. And it's not anywhere near that simple, but that's sort of the idea that we want to kind of move away from. Turing's machines show what can be simulated by mechanical procedures, not what counts as rule following in the full-blooded normative sense Wittgenstein emphasized. Second, it supports a substrate-attentive program. If we want computation to eliminate life or cognition, we should investigate how particular substrates, which are biological or chemical or some other maybe molecular substrate, sustains the pragmatics of rule-governed activity rather than assume that symbol crunching is enough. Finally, it reframes Church-Turing as a hinge, mathematically indispensable but philosophically non-final. To keep meaning in view, we must, as Wittgenstein urged, go right down to the foundations, not to replace Turing, but to understand what his great inventions do, and crucially, what they do not do by itself decide. So this is kind of touching on the decidability criterion of Church-Turing. And so, a lot of that is kind of embedded in kind of the way we think about, things like teleology and decision making. And we don't want to ascribe something to any system, whether it be a computational system or a biological system. Okay. So that was that article. That was a nice article, I think, for, I think it was a nice tour of sort of the philosophy around that issue, and it brings up more questions than answers in a lot of ways, but it gets to a nice point, I think.
Yeah, hi.
Hi.
And I just came in at the very end, and if you don't, I feel very selfish asking this question, but is there any way you could like summarize the article that was there? Because I just saw the end of it. I was like, yeah, that looks really interesting. So I don't want to make you go back and do everything, but I don't.
Oh,
Either a quick
yeah,
summary or
maybe it
just
deserves a summary.
yeah.
Yeah, so this is what does computing mean? This is from Complexity Cat, um, and the author is Amahury Diaz. And this is basically an essay about the major epistemological gaps surrounding the concept of computation that have been sort of ignored in this debate uh, about how you can apply the idea of computation to life, so like biology or the brain. So we talked about this back when we talked about physical computation, but we've also talked about this in terms of applying the metaphor of computation. And so one of the things in this article is that, you know, we have this metaphor, and the metaphor is, has some power, but it doesn't have the power to sort of instantiate itself. In other words, you can't just, conjure up this formal computational set of rules and say that life follows this computational set of rules, and therefore we can understand it as computation and we can replicate it in a computer when it may not be computation that you're looking at. It's just rule following, or it's just sort of a regularity that nature is um, producing, and you're interpreting it as in the context of our ascribed rules to it. So the power of metaphor only goes so far, and the whole point of that article was to point out that there are a lot of, if we go back to some debates back in the 30s and 40s and even 60s, people were thinking about this. And it's kind of, that debate has kind of been subsumed by people just applying the idea of or assuming the idea of pancomputationalism, which is this idea that computation exists in nature and in machines, and they're just sort of the same definition, and we can make a clean transition between the two.
Yeah. Okay. Thank you. And I don't know this is in relation to things I posted in Cognition Futures or not that it came up, but it does definitely fit some stuff that I've been exposed to this week. And I have. Was that just something that you wanted to talk about, or like how did it come up that you got to that?
Oh, I found this article and I just decided to go through it, and so it's
Okay.
Yeah.
Then I will. I don't know what you wanted to talk about next, but I have a relevant segue of sorts.
Yeah, why don't we do that, and then I would like to talk about your stuff that you wanted to go over.
Okay. And I didn't, Emma, for talking about that. I had really wanted to have like a website or something I could point to about it because it's there. I haven't had time. I've got sick this week, and a lot of things had to be rescheduled, so I don't have as much of that as I'd like. But we can certainly talk about that, especially if I might get to my notes about these things. The first, the direct connection to all of that, which I posted in Cognition Futures. There was a meeting. Well, I guess I posted one of the things from it, but there's a really here in I don't know how to. It's not really entirely defined yet, but there's sort of a new group in the area, and it's going by the Computational Philosophy Club at MIT, I guess, but not necessarily exclusive to that. And it's related to some things that I've mentioned before. But the meeting this week, the first half of the meeting was a discussion between Joseph Bach Will Hahn and Elon Barinholtz. The latter two are part of Florida Atlantic and the Complexity Center and Mind Center, and are professors there. And Joshua is, I think, his main affiliation now is the California Institute for basically machine intelligence or machine it's an AI research institute in California. It was interesting because one of the things that came up in the discussion was like East Coast versus West Coast, basically San Francisco or the Bay Area versus Boston, and their take on things. But more to the point of this, it was a lot of talk on computation, and the club itself is sort of this loose computational philosophy bent, but it was also potentially going to be like called the olfactory club because it's interested in this sort of a good portion of the presenters were people doing things around scent or sensing, basically, and how does that relate to computation or ideas or whatnot. I know that Ecolopto, which is what the association of the main supporting group is, has a very particular interest in like olfactory or sense-based language and all of that stuff. But interesting ties to it kind of go to the first half, the second half of the event. To report on it was a few different people having very interesting. One of them was this. One of the presenters was actually basing their research project off of a Japanese ancient Japanese incense smelling or identifying game. I think called it's still related to the Genji story, and they called their thing like Genji Go or Genji Go. And it was something about it's also interesting, really phenomenological ties to go in that direction for a moment, because what I thought of a lot of our discussions on Varela and Depraz and becoming aware and bringing this rigor to phenomenological experience. And then recently at the other event at the summit, also the summit post is up. I shared that in the Slack, but I've kind of talked about that at length, but I distill a lot of my ideas in there. We can perhaps talk about that later also. But at the summit was Andres Gomez Nielsen from the Qualia Research Institute, and there were some interesting conversations that I had and others had with him around basically doing the work of how do you document sort of the first person experience and making it kind of bridging, like Varela and his descendants did, bridging the rigor into that space. So it was, but that came up a little bit there. That's one of my questions for the presenter. I believe it was Awu Chen, I believe is his name. But he's originally from Japan and Kyoto, and has a lineage, or not a lineage, but he's a like very famous traditional practices of incense that he was exposed to. What were informative in this, but it's very interesting because it was sort of like creating this I don't want to say ad hoc, but this unique structure based somewhat off of older Genji practices of identifying the ways that we can experience the layering of scent, or the layering of different sensory and scent olfactory stimuli and approaching. So there's a lot of interesting stuff there. That's a bit of it. That was sort of the second half of the meeting, and there was other cool presentations as well, including various things about that kind of work. But the first half of it with the Joshua Bach and Ilan and Will was very interesting in the computational sense of what one. I'll just share one thing because it's the easiest thing I can share, and it's pretty much at hand. Yeah. Yeah. Let me do this. Apologies for this. Okay, here we go. Yeah, I think this works. Sure. Oh, no, I can't get to it. All right, anyway, so here's sort of the event specifically. These folks were there, it was that time. The video's up now for that. One of them was from Joshua Bach, this universality hypothesis, the structure of the model depends on the mathematical problem of the algorithm's data architecture. And I feel like it's interesting to kind of compare, there should be some other ones here too that aren't showing up. It's interesting to compare, we kind of talked about this binding problem, but not as much as I hoped, honestly. It kind of became Joshua Bach talked about a lot of ideas, which is fine. But I wanted to talk a little bit more about this, what Elon's getting at in terms of one of the things that Elon has is sort of this he's examining a lot of what do LLMs really tell us about language and structure, all this stuff. And I forget what it's specifically called, but he has a video. He gets at one of his core ideas of whose problem is like the mind-body problem or something like that. And his conclusion is it's the problem of language. And so he's kind of approaching. It's interesting to me because Elon seems very. He's very celebratory of large language models and they can understand so much and they can do so much, and that's obviously true in some cases. But he's also a cognitive scientist, but he's also not quite the gadfly or critic that Gary Marcus is about certain things.
Yeah.
So his stance is he takes in this stance of I don't know, like I'm trying to understand his stance, not necessarily because I'm a diehard believer of it. It's much more a sense of I'm really curious at what the fruit of what he's attempting to get at about it is. And that's why I kind of wanted to see more about this specifically, the binding problem and what he's trying to prove with it. Like there was one thing that I do think is relevant, which is here's one of the things that this came up and was agreed with by folks, but Bach said the existence of LM should show that you can learn causal structures from linguistic symbolic symbols alone. That should have been a surprise to a lot of linguists and philosophers. And it's like I'm curious how I feel about that because I don't quite know yet. In the sense of I do think there's sort of a reckoning at hand for a lot of. I think a disagreement between Bach and potentially Elon Barinholtz and like Gary Marcus or some other people is Marcus is very bent on like you for those who aren't who Bradley will know what I mean right away, but for those who are watching, a few years ago, I think around 2020, 21, when there was those AI debates, right? Marcus was holding these like AI debate 1, AI debate 2, AI debate 3, and some of them were debates, some of them were more presenting alternatives to like heavy deep learning, I guess, or just critical of mainstream stuff at the time and whatnot. And one of the things was like the future is hybrid, like this really heavy focus on hybrid systems as in the necessity of certain symbolic logic to sort of ground or complement deep learning things, and how do we make these hybrid architectures and so on and so forth. And I think it's very interesting to see, Richard Sutton and then the bitter lesson came up here, as it does in a lot of these conversations. And it's really, it's interesting to kind of see where things are playing out in this space relative to, and the bitter lesson is basically not trying to hard code specific expertise, and more broadly focusing on what can computation, what is how do you continue to pursue the like, I don't really want to use the word first principles, but like the complete, the nature of computation itself, as opposed to trying to optimize what are tenable or discrete chunks of it to specific measures or metrics. And maybe that's not really the best way to say it. So if you want to jump in or clarify that, you're welcome to do that. But in the context of this discussion, in the context of the computation, again, I missed a lot of it. The post. I'm wondering to kind of go back to the posting to mention it. I really wonder about that too. Like I will make an admission that or confession, I suppose is better. I remember getting really excited when I saw, I think it was like MIT Center for Brains, Minds, and Machine, or something, probably the better part of a decade ago, when I first applied or something with them about like, oh yeah, computation, and it means this, and this is what it's doing, and so on. And it was the way it was framed on the website was like really kind of clear at the time to me, like, okay, that makes sense. And now the sort of this, there's an upcoming event. Yeah, hold on a second. Yeah, there's an upcoming event next week with a similar group of the eclectic folks with Will Hahn and Baron Holtz will be in San Francisco, blah blah blah, and the topic is a technical conversation about reinterpreting civilizations, all those questions, whatever, models, framework, ideas, rituals under the framework of modern computation. And I think that's kind of a, modern computation is both a thing, but also a way by which, if you have something computation, like in a sense, in essence, computation, to have your computational model of it is a little bit like, well, do you have the AI? Are you using AI or not? In a very in one sense, and not the whole sense, and I'm not trying to discredit computation by saying this, there's sort of an element of, well, if it doesn't have a computational component and you're not doing a computational modeling of it, then what are you doing? Like you've gotta find a way to bring computation in, otherwise you're just not respected in certain ways in life, and that's I'm being loose and fast in my usage of that. But what I said about this event is like, I would like to submit a particular section discussion identifying that which cannot be understood or interpreted well via computation, and in particular, how it relates to or deviates from cognitive science, as in like hexagonal traditional cog sci, and its attempt to unify things, neuroscience, AI, philosophy, anthropology, whatever, via computation. And sort of the cognitive science project into the 50s, 60s, and beyond, and where that went or not, and how it's sort of relationship to go all the way back now to linguistics and to computation. And I always, we've had many conversations here about, is there even at institutions I've been at, what endured wasn't even the cognitive science; it was a cognitive science minor in the linguistics department. And just to kind of run out full circles, like, yeah, like you have the analogy of computation that does work, and you have actual computation, and you're kind of in this space of, what is it? What are you trying to get at? And there's sort of this. I think my last point will basically be, there's a sort of necessary humility to realizing the convenience or readiness of certain analogies, um, versus the function of what it's doing. And I find that to be, I'm assuming some of the article that you originally came all this up with that you presented is kind of addressing that based off of what you said. Like, where does the analogy hold or kind of fade out the metaphor?
Yeah, this is great because this dovetails quite nicely with this article. So, one of the things they talked about in the article is so this thing up at the top of your screen that you're sharing at the 1 hour 5 minute mark. It says universality hypothesis. The structure of the model depends on the mathematical problem, not the algorithm, data, or architecture. And there was this part in the article where they talked about, is computation, when we say that, like say life where the brain is computing something, are we talking about some actual computational structure, some sort of natural structure like we observe in mathematics and we celebrate in mathematics, or is it just an artifact of our rules that we apply to the system? So do we say like if we apply an algorithm to some biological process, we get out an answer that looks like it's um, that it conforms to the algorithm that solves a problem, but really we're just applying a computational mathematical cultural practice or cultural set of rules to a natural system. It's kind of like when we analyze something with statistics, and we either we get an interesting result, or sometimes we get something that is a spurious result, um, and we have to distinguish between the two. Um, yeah, I mean, I'm a little confused in how to make that distinction, but I think that they're going in the same direction. They're considering the same set of issues, which I think is really interesting, without any reference to any of the readings that we had in the article. So they don't talk about Wittgenstein or Turing, but they're just basically saying, yeah, these are problems, and let's talk about them. Um, this universality hunch. This is also one of your posts. Model structures may converge more on problems and architectures. So, I mean, if you take that another way, you could say that model structures kind of converge maybe upon function. Yeah, I just think that there are a lot of connections here. Really interesting work. So, yeah, that's something we should check out more. Yeah.
Yeah. Sorry, I'm sorting myself out here for something else. I'm trying to get to something that I wanted to talk about for the what I'm doing with JoPro. I don't know if you want to do that right now or you want to come back to it in a.
Yeah, we can do that now. We can talk about JoPro.
Okay. All right. No, that's not that. Okay. Turn this off. I don't think I can share anything today. Oh, before let me there was a concluding thought that I had about this. I don't know, it escapes me. So I'll let it go. But as far as JoPro, it's been a really good week of refining what I want. I don't have anything visual yet to show about it. But one of the things that a key theme that's sort of related to what we were talking about, and a little bit about the universality hypothesis stuff, is I had a discussion. Maybe what I'll do in place of it is I don't know. It's not really what I wanted to talk about. It's easy to talk about, but it's not quite what I really wanted things to be, and things are loading slowly here. So maybe I'll for like a very I'll do a very poor. Okay, maybe it's loading. But what I was gonna mention that does fit at large within the broader confines of what I'm trying to do with it, currently named Future Studies Center. I had a discussion with I suppose a few people this week because it came up in the data and direction internship. One of our interns is focusing on AI and quality and education, and one of the articles in that one of the articles that we came across in that process, I think I might have found it, was a Atlantic or Time article that was written from the point of view of a high schooler, basically saying, AI is making us less good at being students, making us procrastinate more. It enables there's more to the article, but we basically only talked about the first couple paragraphs of it. And I'm not saying this is what the student thinks. I'm just mentioning this to abstract out a very specific topic of discussion, which is one of the conclusions of the first section of the article was. I'm trying to pull it up here. Actually, it might be really easy to find it this way. So one more second here. It was essentially discussing. Basically, the conclusion of the article got something along the lines of the kid who's a high schooler, and I think it's very important. I think it's very important to emphasize it's written from the point of view of someone who is not even yet gone to college and has been exposed to certain things. But their point was saying, I think there's sort of a downward pressure on the quality of education because deadlines don't matter. You can procrastinate. The discipline. One of the lines was very much the discipline of having to do complicated things within a short timeline is now lost. Like that pressure to learn that kind of discipline has been taken away, and now we're all there's a negative outcome from that. And what it led to was a Birch Brothers discussion on, at least for me, philosophically, and this came up in some other. I have a colleague of mine who is doing a program in systemic change, behavior and systemic change, and it's very interesting, like as a applied like graduate coursework. And it's very interesting to have a conversation with all of us around this, in the sense of what I wanted to abstract from this particular topic. And I will eventually tie this a bit into future study stuff more. But and more conventionally, this conversation would be under the sort of so. I think I've very reached for a name of as ingenious as like the educational banner of orthogonal lab. Like this group, this really meaningful, but never really defined discussion space that we often come back to about how are we teaching, how are we doing, not just project manager, but the pedagogy, the nature of trying to educate or create spaces for folks to do the learning, all that kind of stuff. Again, to go back to the article where the student is saying, yeah, we're losing this opportunity to build this very important discipline of XYZ. And when I first read the article, my honest reaction, and again, I'm a bit privileged, but also there's a bit of privilege to it, and there's a bit of very intentional pedagogical selection that circumvents some of the problem in the following way. And my initial reaction was, geez, I totally get, and there's a very real value to discipline, and I think that's especially true. I'll put it this way: discipline relative to here is a deadline, find a way to make it work. There is something that will only come through that particular lens, and I'm not out on it. But and this is why I say I think this is something that a student would definitely not really know yet unless they were intentionally exposed to it, as in a high schooler or a 15, 16, 17-year-old person. I had such a strong visceral reaction to seeing the language of the article because it's like, oh, well, I I'm running internship right now, and I've been a part of this myself, but I've successfully done it and created a situation that has no timeline of any real consequence, and the discipline is very strong. The discipline that which we are trying to achieve or build or cultivate or make as pedagogical educational space, the skill development comes because people want to do the thing. They want, you could say, intrinsic motivation, but also, um, I, I, I kind of, I shirk or shrink or recoil. Um, I recoil a little bit at the intrinsic versus extrinsic motivation, centering what I'm trying to say, because yes, that is a valid lens, but I think there's something more to it in the sense of, and particularly in the data indirection stuff, which interns that I'm referencing, but not just them, other things. Um, it's because people see the need, and because they believe that what they're trying to do matters. They realize that discipline isn't something external to just be adhered to or comply or satisfy, to just not to avoid the negative. I don't want to be. I want to do well, and I don't want to get punished. I don't want to fail. I don't want to get a bad grade, so I'm going to do it. Versus, I want to make this change in the world, or I want to make money from this, or I want to succeed, or I want to generate something of value. It could be moral value or non-moral value. I want to do something of value to me in the world, which necessitates the discipline. And even also, you can I didn't talk about this at all, but there's a whole other aspect of this, which is like there is also a discipline in play when you are actually enjoying it and you're wanting to experience or do the thing that is not even productive, not even about value generation, but just there is a discipline to to the earnest engagement of the subject matter. Um, so the discussions that kind of came up this week around this topic, and one of them was in this came in a few different domains. Some of them data and direction itself, because we were talking about the article, but then also systemic change, pedagogy, education, and whatnot. Was just similar in a very. This is a very big stretch, and I acknowledge this, but similar to the universality hypothesis of the structure of the model depends on the mathematical problem, not algorithm, data, or structure architecture. I find the discipline issue to be a very interesting. Um, when you look at the issue of discipline, and I'll even say, I don't know if I want to call it a skill, but something that's the the useful quality that is having or developing or cultivating discipline. I think it's very interesting to consider in a purely purely abstracted pedagogical sense. Yes, there are many different ways that you can present a student to v- willingly engage in developing discipline about something. Um, that's a nice sort of really highbrow, not even ivory tower, but just like kind of pristine point of view, and a much more gritty reality, touching the ground, touching the grass, touching the reality of the situation. We are, and this is very much centered in what we're looking at in some of the AI and education stuff. Um, you we are forced to deal with a reality where some of the causal let's say incentive structures around teaching are not as applicable as they were. Like there was a time when you it was just you, and your tablet, your in Rome, your ancient wax tablet. It was that, and maybe some scriptures, some scrolls. That was it. You did not have Chat GTP. You could talk to some folks and read your stuff, and that was what you were there. And so, hey, you better do this. It's going to take you time to read. It's going to take you time to write. It's going to take you time to, redo your wax tablet. It's going to take you time to, like there was just inevitabilities of what that process did, and different incentives and logistics that made certain approaches de facto the best ones available, or the only ones that were tenable to do certain things. And that's different now. And one of the things we're looking at in data and direction in particular is the choice of how much you can choose, the ability to opt into, an AI dominated classroom versus an AI free classroom, a phone free classroom. And there's all these different economics and pressures and teachers and being overworked and all like those kind of things. But at the level of what do we do about the problem of discipline? We're in a situation where maybe the incentive structure of here's a 2 week deadline. Um, you've only got 2 weeks. You better do this. Um, Maybe it's just not going to hold the same weight. Um, for better or worse. I'm not really taking a normative stance on this. I can take a normative stance, but I'm not interested in that right now. It's more of a sense of identifying if a goal, if something we want to highlight is the development of discipline. How do we acknowledge that 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 the environment and the incentives and sort of the pressure or the pedagogical like structuring of situation maybe um, is different now. And my final caveat is saying, yes, I'm in a very luxurious position with data and direction and other things where I've heavily selected for people that want to have a certain passion in a topic that's both somewhat monetarily feasible and morally compelling. And that is not the same as your sophomore mathematics class for most people, or your let's read about um, what some guy in the 17th or 18th century wrote that has no real direct connection to your life right now. You can say the work of a teacher is doing all that stuff, but I'm just acknowledging a certain what I'm sort of loftily suggesting or alluding to, I know is not feasible for your generic, uh, everyday, any town USA strapped, overworked teacher that isn't going to necessarily get to like your typical, like your Freedom Writers inspirational movie level of capturing some kind of a meaning and all this other stuff. So we're to kind of I'll make this point and then have room for comment or whatever. But basically, how I mentioned this situation because I just did a super kind of hand wavy, even honestly. I did a very general discussion of discipline, of how something was brought up, how it's implied in its education, and kind of doing some diagnostics on what's making it's salient. I'm abstracting out the nature of the problem, or the in this case discipline, or like skill building. How do another way of saying the question is like, how do you build, how do you develop skills like discipline in a world where the time burden or a lot of the initial legwork has a very different value. Like you maybe don't need 2 weeks to do the same thing anymore. Like maybe what you want to do is there, and like we're at a slightly soapboxy sense. Like we're totally unprepared for this. Like there's like it's super. It is very plain to me, and I think people. I think I want to try to continue to normalize as much as possible, saying we aren't. There isn't like there isn't a sense of um, the collective big whatever ombudsman you want. You could say the Department of Education, which is like would make you chuckle in some ways, but there's no magical ombudsman, there's no parliamentary structure or ministry that is just keeping the entire slew of teachers on the same page about what to do about all this stuff. Like, this is literally a very heavy hit that is unprepared, like, there's relative chaos about this particular subject. And so I'm saying that not of alarmism, but more like it is appropriate to talk about this like it's a very big sea change and people aren't ready for it. So in the context of all of that, what am I trying to get at here is like, one, the reality is we're in a different era, and whether or not we don't even know if that era is going to continue necessarily, but for the moment, what is available, what is tenable, and how it's going to be used is um, very different and very new. Now, ta and my conclusion for this is basically the problem of discipline is interesting in and of itself. The sort of proposed or interesting or lofty solution that I have is about it is sort of, well, I think there's something to getting people to find a way to build what they want to build. Like, how do you get them to having, you could say flipped classroom, you could say incentive, you could say intrinsic motivation, but how do you get them to think that it matters not just to have discipline, but to show them a meaningful way that what they want to do inherently requires this discipline. And that's great. To zoom it out even further, what I'd like to do in some aspects of the future studies is identify this type of thing across various domains, um, particularly education, particularly knowledge generation, particularly how science and education work, particularly the sort of inherent. One of the things I really want to look at in the Future Studies Center is this: how are we, a very sober assessment of, and I kind of even tried to get at this in the original part of my talk, and I don't think I did a good job about the previous topic, was how are we very aware of what is making certain approaches or views tenable, and how does that change? Like, why, like I really examining, to use the discipline thing as sort of this easily very accessible topic. Like, why what I would have loved, and I haven't fully read the article, I certainly haven't talked to the author, but I would love to say to them, like, yes, um, the means by which you have been shown to develop the skill set of around discipline has become disincentivized. Like, the pressure to do it that way is less now. And I would love to ask them, how do you think you will, like, where do you want to go? Like, is it a valuable thing for you to learn? But also, like, how do you see yourself as acquiring this or being in a space where you want to develop discipline? Um, Whatever that particularly means. And I don't know. I think there's a space for bringing a bit of rigor and a bit of inherent, like, almost meta-scientific philosophy and history of the fields, and then really trying to map out where the alternatives lie. Like, okay, the prescriptive, and I'm not going to go, I'm not going to, I'm for a viewer that we won't understand the context of this, but that's okay. I'm just going to kind of wrap up here and say, for the descriptive part of the future center things, you could do this documentation of what has been and why. For the prescriptive part of it, you might have these suggestions about where it can go. Like, what are these alternatives? Like, how do you center project-based learning, or particularly projects, some the building of something in the world that's somewhat tied to a meaning or value, and how much can you afford doing the work of actually trying to know what that is? Like, in a very ideal different world, maybe you're having almost like intake with your students, and you understand what is their disconnect about feeling agency and autonomy and the ability to build. Like those are related components, but in the way that education is currently structured, we don't. We, your job as a teacher isn't to have an intake and a therapy session with them. That's silly. That's totally not the case. Even if maybe it actually is, but in conventional stuff, that's not what you're supposed to do. This isn't Dead Poet Society. That's for the movies, and the tension is there. So that's this isn't. I don't think I will conclude here, and I don't think my project and what I've just said really holds a lot of weight or sounds. Um, it's not a great showing for what I want to do when I'm talking about the future center, but it's a very relevant discussion that happened this week. And I think talking about discipline in high school education is nice, but I don't want the future center to be just about that. I kind of try to use it as an example of some of the framework and lenses I'm trying to flesh out. Um, at a very small scale and a very accessible topic. So I don't know. I'm open to any questions or comments on that. And I know that was maybe an unusual discussion, but yeah. Any thoughts?
Oh, I I think that was a great discussion. Thinking about how we change the way we learn using technology or using just methods that we kind of adopt that improve things or maybe don't improve things. Or in this case, you're talking about having discipline or the value of doing something under a certain set of conditions. Like it's the pedagogical aspect where I'm gonna blindfold you and you have to like feel inside a box and learn what those things are inside the box, right? And then that's or like in the Karate Kid movies where he teaches them how to make movements that are sort of related to the different karate moves, but it's trivial things like sanding the floor or waxing a car or something like that. So there is this aspect of discipline, and how do we achieve discipline, so we can learn things when we're not in the classroom, where we might um, need to transfer our ability to learn to a new domain.
Mm-hmm.
I have two questions though. The first one is, you remember several years ago, I guess now, you used to talk about mastery, and then we had this whole discussion about how that fits into cybernetics, and there was a lot of discussion about cybernetics and mastery and all that. And so, what is the relationship between discipline and mastery?
Yeah. Can you can you refresh me a little bit of some of those discussions, because it sounds really cool, honestly, and it doesn't trigger, like, I feel like I'm out the door, but I can't look inside the room yet. So can you tell me a little bit about what those discussions were?
Well, as I recall, there was this theme in cybernetics, and I can't remember who. It could have been Norbert Wiener and some of his stuff that he talked about. So he talked about education, he talked about other things, and there was this aspect of mastery or mastering certain domains of knowledge, and how do you do that? And I guess this is relevant to learning, artificial learning as well as biological learning, in that you have to learn about a domain, right? So the more you learn about the domain, the more it becomes sort of part of your automatic behavior. You then master that thing, so you can reference anything that you kind of encounter. So, like, when you meet people who've been doing academic research in a certain field for like 40 years, they can come up with different references and they can come up with different like points of view immediately, whereas a new person they might struggle to find the right answer, or they might It might take them a while to make the connections. Now that is to say, I don't know how much we could do build a cybernetic model of mastery, but there is this aspect of like, what does it take to become a master, right? It's expertise, but in practice, maybe it's a long-term perspective. So, like, do we need? I guess another way to phrase my question is: do we need discipline, or certain types of discipline? Are they required for mastery, or is this just something that we can, it's just a different kind of process?
Okay, and you mean that makes sense. Thank you. And when you're saying, just I kind of think I know this, but just to ask you the question at face value, when you're saying discipline, I assume you mean like the discipline that I was talking about in the other thing, like. Go ahead.
Yeah, like developing like the ability to think under pressure or to think in a certain amount of time.
Yeah, it's so interesting because, like, even the word discipline, I think in a lot of modern sense has this sort of militant, Nazi, basic training. You lack discipline, Arnold Schwarzenegger soundbite, and I find it to be, yeah, like there's sort of this, I don't want to say two cultures like divide in like the CP Snow sense, but like a difference between, oh, he's a really disciplined sports football player, or he's a really disciplined mathematician, or he's a really disciplined businessman, or he's a really disciplined artist or writer. He writes all the time, or he's really disciplined to his craft of anything, honestly. And so the broad question here is discipline and its relation to mastery and so on. To say a bit more about discipline first is, I think I don't really like the word discipline for what it's trying to get at in my mind. And maybe it's just because it's loaded and has these connotations or cultural references or whatever. Because, yeah, like when I think of the word discipline, I just think of all these different things that were just said. And then also like the idea of developing a discipline of study too. Like that's a different meaning of the same word. But what I'm trying to get to, and I'm rephrasing your question a little bit so I can try to get to how I interpret the core of it, because I think the core of it is important. So discipline, and sort of this intentional, and I say this acknowledging I'm someone who I grew up as the son of a martial arts teacher, and the cultivation of the skill was very, it requires discipline, but I really see it much more as an earnesty of wanting to know yourself or the thing. Like I actually associate it quite a bit with like the capacity to love in a particular way, like not to be in the feels part of it, but are you actually just I just wrote about this somewhere else, actually, in the context of, at its core, I think it's about, are you rigorously attempting to update your model, in a cybernetic sense, and every good regulator sense, if you will, are you willing to update the states that you can account for and relentlessly, diligently do that? So I don't think discipline is necessarily doing your 50 push-ups or memorizing your multiplication tables or writing 2,000 words a day. I think at its core, like what you want to instill in a pedagogical sense is reverence. Okay. Now I can throw it back to Norbert Wiener. The quote that I've said many times, especially years ago, and you may even were thinking about this, but it's resurfaced now. Something about along the lines of doing scholarly work or being scholastic in its truest sense is more of a consecration or a duty. Like there's a reverence to it as opposed to just a job. Like if you're really trying to learn, there's a certain investment, like a commitment to understanding the edge cases, the outliers, understanding the degree at which the problem is. Like you really getting into and incentivizing. You learn to appreciate the challenge of the domain space, and you consistently show up wanting to know more. Like when you're just. I think there's a discipline, but it is also just in a phenomenological internal learning sense. You have a sense of. I don't think interoception is the right word, but you have a legitimate sense of the problem space being represented adequately or not. A lot of the things I'm interested in, and one of the things I want to do under the banner of the Future Studies Institute is I want to center something that I'm calling Steelman the problem space as opposed to your side of the debate. I want to center how great it can be to really identify and discuss the problem space itself, as opposed to just whatever schools of thought on it. And I think that's a huge paradigmatic shift. We talk a lot about synthetic conferences and designed to not really be synthetic in a lot of their stuff. I'm just vaguely reference that. But like I want there to be a new model of debate. Debate's very popular right now for reasons I'm not even going to get into, but the idea of come debate me and prove me wrong and all this other stuff. And I was like, yeah, that's fine. Like there's something to that. But I think there's also a very legitimate sense of how do you get people to realize there is, I would say, majesty, but there is wonder and exhilaration and goodness and rigor to be had in identifying what the actual domain space is, what the problem is, and in the sense of the universality thesis, as we're calling it right now. Can you identify this problem space across the different domains that it might contain? And how do you engage? How do you have the earnesty of doing that? So we talk about discipline and mastery, to kind of zoom back out again. I feel like it's very much a sense of I'm gonna put on my like coaching hat for a second of like you have to have the buy-in and the desire to care about it. Now, where does that come from, and what can you do about it? Like, there's different roles of I'm in a classroom, I need to get kids to have a baseline minimum reading skill, and we just got to do it, and here's how we're going to do it. That's very different from I have an intern who passed a very rigorous application process, and they know this matters to them, and they just want structure and someone to talk to about something they have in mind. Those are different things, but like depending on where the spectrum you are, how do you incentivize people to pursue those things? Now, and to come all the way back out to like discipline and mastery, I feel like mastery in this context is sort of, you can say discipline across time, and I kind of also had this sort of tangential note of like, well, will we ever get to the state where it's the Matrix and you can download Kung Fu and I know Kung Fu? Like how does that change the thing? And it's like, well, I don't know. We're not really there yet, so we don't have to worry about it. But I do think it's worthy considering. Can mastery be accelerated? Or we've talked before many times about what was it, the minimum viable theory, minimum viable like theoretical knowledge of a domain to do something in its space, and that kind of related to some of the frontier map discussion and other things. epistemological directories of the past. But yeah, I mean, I think it comes down to, I think so much of the work right now, and this is my obvious, like, gigantic personal bias and lean, I think so much of the work right now is clarifying and illuminating relative destination spaces for a theory, an idea, or the outcomes. Like you can say, I want to take this domain space in a direction, or the applied, I want to find things that are going to make this aspect of the world more likely, or this aspect of the world less likely. Whichever of those things, I'm agnostic in this particular point of view. But I think we're in a world where the actual act of building to pursue one of those destinations, or at least like an informed sense of an informed juxtaposed sense in the future center language that I'm building out, alternatives. Like the key word is alternatives. How do you identify an alternative that is meaningful or valuable or tenable or interesting? And you know, how do you go there? Like that requires to do that requires I think it requires discipline. And eventually, ideally, the better it is, the more mastery of the problem space, and mastery not just of the problem space, but of the bridge you're building to reach that problem, that destination, the bridge across the vantage points. My old vantage points article that I should properly publish now. Like, how do you go from the current to the other and translate back and forth so there can be feedback between the vantage points? All these things. So that's probably a bit more. I think you said you had two questions, and I just totally I'm not with one of them. But I don't know. Do you have any thoughts about that? That was a bit of a winding road, as usual.
Well, no, I think that was good. It leads to the second question, and maybe it's more of a comment, which is that, you know, we oftentimes will impose discipline kind of, you know, through how long do we want to take to learn something, or how long do you have to learn something. So in a classroom setting, you know, we'll have deadlines for assignments, and, you know, usually it's like I'll give someone a week or 2 weeks to do something, and I don't expect them to, you know, like, sometimes there's a temptation when I ask you a question to dump like 20 paragraphs, right? Or to write like a very refined answer that is like well researched. But that's not what I'm trying to get at in an assignment like that. What I want to know is, I just want to get your feedback on what I'm asking you. And then, you know, you can have that kind of an assignment, or you can have like a term paper, which is over maybe 3 months, and, you know, you have the entire term to write this. Maybe it's a more refined research paper where I ask you to go get references and engage in a larger structure in the document. So you're maybe asking a question, or you're exploring some topic, but you're giving me a multi-part answer, basically. You know, if I give you like a qualifying exam where, you know, I might say, I'm going to ask you a question, you have 24 hours to answer it. You know, so I mean, I want your answer in 24 hours. Here's a question, you go, you know, answer it, and then send it to me, and I read it. And it's, you know, it doesn't need to be like a well-researched paper. It just needs to be something that shows me that you know some topic. So we have all these structures in education that are kind of disciplinary in that sense. It just gives you like, here's something I want to know. I want to gauge your feedback.
Yes.
And I'm giving you a certain amount of time. And the point is not to like, I mean, the point is to do a good job in that limited amount of time. And if I do this like over time, you know, I should expect like better performance, I guess. But that's not really the point. The point is that I want to like put you in a situation where you have to give me some insight in a small amount of time.
Yes.
Yeah, and so we do that, but it's like, you know, maybe to your point, it's more, it's something that we should use more strategically throughout learning things. that maybe it is a good way to do this, or to sort of deploy it strategically in a way maybe for artificial learning, or if you're talking about a new domain where we need to learn things and we need to gauge like how people are adapting to some new technology. We can see how they perform on those kinds of things and evaluate it.
Yes.
Yeah.
I very much appreciate this comment because there's many things I want to say, and I hope I can say all of them before I forget them. But to jump to one of the more important ones is, I think what we're dealing with is, and I did I alluded to this, but I didn't hit it very well on the first pass. What the advent of ChatGPT does in some ways is we now are forced to, we're more face to face with what the student actually knows or doesn't know. However, the means by which we collect the feedback, collect the prompt the iteration, are different, or can be, whatever. And again, to stay on this, you can get around this by simply just saying, okay, we're not good, nice, thank you for writing your paper, and not in a way, not in a gotcha way, but like in a legitimate way. Thank you for writing your paper. Now, tell me about it. You tell me about the paper and the meaning of what did you learn? The fact that it's generated automatically in 10 seconds doesn't change that if you're trying to communicate the merit of it, you still have to do that. The actual does it change the person? Do they know it? Can they ever comment on it? If it's just, you could, I don't know, you could say haven't looked at the paper or not, but does the person know how to wield whatever it is they're supposed to learn or not? You can't, we're not, at least right now, from what I've seen and what I've experienced, even my own use of it. I use GDP all the time in the internships right now. In part because I'm not interested in the busy work. I don't care about that. I literally want to know, what do you know? What are you trying to build? What are we doing? And I'm not saying that's how teaching should be, because I'm not, as I said many times, I'm making disclaimer many times for purpose, but I'm not in a typical situation, and I've crafted the situation very specifically because I didn't want to be in that situation. But to stay on point, yes, at its core, and I'll step to finish that point again and try to hit it on a different angle is, we still have the challenge of getting to know what a student knows or not. In generic education, where you are trying to verify if a core fundamental feature of something has been ascertained or not. That is GDP doesn't just take that away, it's there, right? And we have the opportunity here is, it's so funny because we have all this stuff about, AI will offer really tailored experiences in learning for the student. And it's do you have really tailored experiences from the educator with the student to facilitate the transmission of the understanding and of the feedback? It's nice that the student can get X, Y, Z, but how is it? Where's the connection to it? What's the complete feedback loop of the whole, the educational ecosystem in the classroom? Right? To put that aside, I think, as you were saying all that, I think another key thing ingrained in what you were saying about the deadlines, the structure, is it this paper, is it eval, is it a term paper, and it's so interesting because I honestly, I'd thought about some of these things, but it wasn't until you said it I felt a very particular difference. And now that I'm doing the teaching, now that someone says, I think someone very nice is like, "Oh, Jesse, happy Teachers Day," and I'm like, "Am I a teacher now? What?" Like it's like, oh, like I'm doing this intern thing. People are saying this way, like, "Oh, I have a master's degree." So, like I was like, it didn't really connect, and it's like I think they were just being nice, based to be honest with you. But there was a sense of hearing you say it and having this sort of camaraderie now of designing some of those things myself, at least in a much more formal way than ever before, is it's so different. And I kind of I had in the discussion, there was this moment of, oh yeah, like I was able to share with you the educational administrative perspective of like, well, we have like 10 weeks. And I got to give them time to sort things out, and I have to break up the time in this ways, and I have to let like some of the short term, some of the long term, some of the in depth. Like you have to vary up what's there. It's like you have to plan it out strategically, like this campaign of my 10-week campaign of education or whatever. And as a student, it's like, well, maybe if you're a really good student, you think about it that way too, more so. But for me, at times, it was mostly like, all right, what do I got to do now? Oh, I got 2 more days. You put it off and that kind of stuff. And so it's very different when you're trying to structure these time boxes for stuff. But what you're getting at is iteration, like the demo or dissect that we talked about, or at least the nature of like, how do you create a meaningful time period for intake, study, processing, and then create a situation for you to give something back to you. And yeah, even acknowledging that it maybe isn't going to be this masterpiece, final product, refined paper output, that's great. But pedagogically, you're trying to get this iterative process just so they do it. Like you have to. This is why it always seems to come back to me to some form of building. Like that's my favorite word lately. But like you have to construct something. And I think I know we've talked about it in a lab all the time, and I would say all the time, oh well, so we've got a blog post, we've got a presentation, it's the importance of this and that, the importance of everything else, the importance of doing it regularly, presenting your ideas, all this stuff. But it has a different layer of meaning to me now, even, which is really like, how do you meaningfully iterate? You know what I mean? Go ahead.
Yeah. Yeah. All right, that's great. Why don't we leave it there? And yeah, I'm interested to hear. Maybe you can put a blog post together on that. That'd be great.
Yes. For next week, what I would like to do, and even I might even just be working on this later today because I finally have time. I finally don't have like this head cold thing that's super like cognitively distorting. For next week, I would like to present sort of, I don't know about one pager, but I would like to present what is the currently named Future Study Center or Future Center or something. And I want to identify the key points. I want to talk about alternatives, destination-based research, descriptive, prescriptive, evaluatory, on-ramps, alternatives, like those have this sort of glossary and the structure of what I'm trying to do. And I'd like to present that next week, and a few other things, but that's sort of my goal. And maybe also, if I had more time today, maybe the interdisciplinary research presentation. But at least some of that for next week.
Okay, well, yeah, we can do that next week.
Okay. Thank you for this stuff, and as usual, please share the links in the chat because I want to go back and look up that. Thank you very much.
All right, sounds good. Thanks. Talk to you later.
Bye.
Bye.